Okay, so let's start with the first public online extreme universe colloquium. So we are very happy to have Professor Koji Terashi from the University of Tokyo. Professor Terashi has been working on physics research in the ATLAS experiment at LHC at CERN, and he has been responsible for searches for new phenomena beyond predictions of the standard model of particle physics. And Professor Terashi is also currently involved in the development of quantum computing application to high-energy physics, mainly on quantum machine learning, charged particle tracking, and quantum circuit optimization. So today, we hear tell us about his recent works on quantum algorithm and qubit technology applications for particle physics. So Professor Terashi, please start.
Yes, okay, yeah. Thank you very much for giving me the opportunity to talk about what we are doing here at ICEP, which means the International Center for Elementary Particle Physics, the University of Tokyo. So as Nishoka Sensei mentioned, in this talk, I somehow try to highlight the recent work in our group, not just by me, but number of people working on that in ICEP. And actually, as he mentioned, we started working on quantum, particularly aiming at application to high-energy physics experiments, like processing large amount of data or charged particle tracking in experiments, so on. But these days, we are exploring not just for experimental application, but also for kind of theoretical studies, and also trying to use the qubit technology for particle physics experiment, like using the quantum device, a qubit device. So I want to talk about that in this talk. Okay, so maybe just starting from a kind of a high-level picture of what we are interested in. So as you see, okay, on the right-hand side, you see the picture of the history of the universe. And as you may all know, we are the 130 billion years after the birth of the universe. Then if we just going backward in time, so some structure was formulated in universe. Then going further, there is the epoch of the recombination, where we see kind of a remnant from the Big Bang of the universe. But even going further, there is epoch of the formation of the nuclei and also the formation of the nucleons. Then going further, we are in the era of quarks and gluons and so on, more fundamental particles in the universe. So then in that era, you see that these accelerators may be able to play a significant role to find just a constraint, an interaction between the constraint matters and gauge field, so on. So that somehow motivates us why we consider accelerator for this physics. But anyway, so the particle physics is actually aiming to answer all these kind of a big question: what is the origin and future of the universe? What is the nature of elementary particles? How do they interact with each other? So on. So actually, particle physics is trying to address why the universe is like the one we see right now. So that is kind of quite high level question that we are all interested in. So in order to do this, one approach that we consider interesting is to use high energy accelerator. So on the right hand side, you see the picture of the accelerator. But actually, the accelerator is underground, so we cannot see it. But this is a Large Hadron Collider at CERN, which is the European Organization of Nuclear Physics. And this accelerator is called Large Hadron Collider, which has a circumference of about 27 kilometers. Then it collides the protons at the energy of the center of mass energy of about 14 TeV. So the reason why we consider this is a very powerful accelerator to directly collide the proton, but actually the colliding the constraint quarks inside the proton at very high energy. So then we can directly probe the fundamental constraint in the nature. So then by using this accelerator, we can hopefully probe the epoch of the birth of the universe, because as you know, if you observe the universe by telescope, we cannot go much further in the universe in the history because due to the quarks and gluons in the early universe. But since accelerator can directly probe such fundamental constraint, we might be able to address why the universe was born like that and why we live in that space. So that is why we are interested in accelerator. But actually, if we consider the quantum science, the quantum information technology, we might be able to address kind of a different question from my opinion. But anyway, for the particle physics, we know that this particle physics is the fundamental science to understand the properties, the dynamics of elementary particles and nuclear matters. That we know that this particle physics is governed by these gauge groups, U1 cross SU2 electroweak force, and SU3 for QCD. And then at the core of the particle physics is the quantum field theory, the QFT. Then the quantum mechanics is the foundation of QFT. So since quantum computer is kind of operating under the principle of quantum mechanics, this kind of a device, quantum computer, may offer the unique opportunity for us to probe a phenomena governed by particle physics, because the foundation is the QFT, and that is essentially controlled by quantum mechanics. So that's why we think that quantum computer is quite kind of interesting and promising device to go further in the particle physics. Then actually, I personally think that quantum computer may be able to address the slightly different question from accelerator physics. Like we know that going back in the universe, we know several interesting epochs in the universe, like a Higgs condensation or core confinement, which is observed as the observed kind of trace in the universe. But by using a quantum computer, we might be able to know more about this kind of phenomena. And also, if we can exploit some quantum resources like superconducting qubit, which I will explain later, we might be able to reach beyond the conventional experimental technique, like accelerator. So by exploiting this kind of a new information processing capability, we might be able to address how the universe actually became like the one we see now. So that, I think, is one of the question which hopefully we all are interested in. So here, so this is the outline of my my talk. So as I said before, I'm going to present our recent study that I said that utilize quantum resources, particularly for the application to particle physics. And then I think there are three areas. The one is the quantum machine learning. So the learning the quantum state and processes. The second is the quantum simulation. So this is to simulate some dynamics in the lattice gauge theory, for example. And the third one is the quantum sensing so we can use the quantum device to search for dark matter, for example. So I'm going to highlight what we are doing here at ICE for this. Okay, so the starting with the machine learning. So we use a quantum computer or some quantum circuit to manipulate some quantum state. So by exploiting this capability, we can learn some quantum state or some quantum processes by using quantum computer. But for example, in this classification task, this is a general description of machine learning, not necessarily quantum, but it's a learning task. We are given some data set, like X is the input data, the Y is the label corresponding to that data. In that case, X is either classical or quantum. Then we consider some hypotheses which predict this true label Y from input X in the dataset. Then define the loss function L, which quantify the difference between the label and the prediction to the hypothesis. Then the idea of the machine learning is to minimize this training error, which is defined, in this case, defined as the average of the loss function over the data set. So this is just a general description of the machine learning for classification tasks, for example. But in order to apply this to the quantum settings, obviously the optimization is crucial of these trainable parameters. And also for the quantum state, we need to prepare the quantum state that can faithfully reflect the correlation between the input data. So that is the key process for learning tasks. And one approach for doing this, and a kind of popular approach, is to use the variation method. So for example, we prepare some input or reference state, get psi 0, then apply some needed operators which depend on the input data X. In that case, is get psi in is prepared input state for classical data, or for the quantum case, some wave function from quantum system may be just the input state. Then apply some parameterized needed operators, U or theta, to generate parameterize the quantum state, get psi theta, to the input state. Then usually we compare the desired quantum state by optimizing the parameter theta by using the classical computer. Then measure some observable to calculate the expectation value with optimized parameters. So this is one of the most typical approach for variation method, where we use both quantum and the classical machine to optimize the trainable parameters in the quantum circuit. And this is generally considered to be suitable for near-term quantum devices because essentially we use the quantum computer only to prepare some quantum state and measure some observable under that quantum state. Then all this parameter optimization step is performed using classical computer. So this is more suitable for near-term quantum device where the number of qubits is limited, the coherence time is limited, and so on. Then this is rather general, so this is applicable to a wide range of problems, like quantum simulation for ground state estimation, like VQE, a variation quantum eigensolver, or quantum machine learning problem. So this is one typical setup that we can use for this kind of variation method. So for example, we try to run some classical data. For example, some output from detectors in the high energy physics experiment, then put that into this data encoding unitary, then get some quantum state, then apply the parameterized quantum circuit, then measure some qubits to calculate some expectation value, which is the loss function of the machine learning task. Actually, this is what we did before when we started working on quantum science a few years ago, and we tried to classify some physics events of interest from background using some data similar to what we get from detectors, for example, the Atlas experiment at LHC. So this is just a benchmark, so you don't need to know the details about those processes, but the idea here was to somehow select this kind of signal event on the left from background on the right, which has a similar final state, but kind of different composition in the intermediate processes. The right-hand plot showing the vertical axis is the area under the log curve, which is how accurately this model can classify signal from background. The vertical axis is the number of events used in the training. So then green line corresponds to the result we get from a quantum algorithm compared to the classical machine learning technique. So at that point, actually this was a quite early attempt, but this looks rather encouraging because you see that the performance of classical machine learning seems to be almost comparable or even sometimes even better when the training data set is small. But for the last couple of years, we know that this variation method generally has some limitation in the scalability to large-scale problem due to the infamous Pareto plateau problem, which I will describe later. But anyway, this is what we started on quantum machine learning. Then for us, actually, another interesting approach is to directly use the quantum data rather than the quantum state encoded from classical data. So so here the idea is to directly learn the quantum state without classical measurement, without encoding the classical data. Like in this setting, actually, we will probably be able to extract some entanglement properties of a quantum system, or to determine the classical parameters that control a physical system. For example, the Hamiltonian parameters. So this is a typical setting for Hamiltonian learning problem. Yeah, then for example, we consider some quantum states from another quantum system as input, like this sort of wave function from some other system. Or we might be able to extract some quantum information from another quantum device, like a quantum sensor, by using transduction technique, maybe in the future. But then put that in a quantum state into the parameterized quantum circuit, then do some machine learning tasks to extract information about the input quantum state. So except the encoding part, the rest of the machine learning part, like this parameterized unitary, is very similar to the previous example. And here the one example that we did for the last year or so. So we try to generate some quantum state from quantum simulation in the lattice gauge theory, then put those states into the quantum circuit to identify the phases of the quantum states. Like for example, on the top one is the ground state of the one-dimensional U1 lattice gauge theory, which is a Schwinger model. Then producing the quantum ground state, then put that in the quantum circuit, then to identify the phase transition between the symmetry breaking and symmetry conserving phases in the physical parameter space of the Schwinger model. For the quantum circuit, we use the quantum convolutional neural networks, which composed of convolution layers, which use, in this case, kind of a 2-qubit SU4 unitary gate, with the parameters are common in the same layer. The next layer is the pooling layer, which kind of trace out part of the qubit or just measure it. Then use the rest of the qubit for the following layers. Then by repeating these convolution pooling layers, we end up with, in this example, just 2 qubit. Then measure those 2 qubit state under some observable, like the Z operator, something like that. Then by using this quantum circuit, we try to identify these different phases for the one-dimensional U1 gauge theory or one-dimensional Z2 gauge theory, and also the another phenomenological quantum state, which simulate so-called Parton shower in the high-energy physics experiment. So this is a bit more explanation about what we did for Schwinger model case. So that is Hamiltonian after the Jordan-Wigner transformation. the first term corresponds to the electric field. The second term is a kinetic term. The last term is the fermion mass term for this Schwinger model. Then due to this presence of this topological theta term, there is a phase transition in the continuum limit. The shown on the right is the parameter space. So the vertical axis is the parameter theta divided by 2 pi. The horizontal axis is the mass parameter. Then in this phase, there is the phase transition at a certain critical mass. Then at the same theta value, there is a phase transition actually between the symmetry preserving and symmetry violating phases. And here, this benchmark is still rather simple because we consider only 8 qubits, the 8-side system. Then but the gauge field is completely removed by applying the Gauss law constraint. Then this A is the lattice spacing, G is the coupling constant. The theta is chosen to be pi, so that we are on this on this line. Then generate some quantum ground state using variational quantum eigensolver for different values of the mass parameter between -2 and 2. Then try to recognize these two phases. Then put a label, like if mass is above the critical mass, the label corresponds to 1, and -1 if the mass is less than this critical mass. Then try to identify these two phases. That is the result. Since the system is still quite small, this transition is not completely sharp, but kind of more broad. But you see some transition behavior at the critical mass. This dashed line corresponds to the exact mass, which we calculate using the exact diagonalization. Then blue point from training data. So we train the quantum circuit using this blue point. Then use this test data, which is the orange point, to classify whether that state belongs to which phases between around this phase boundary. So yeah, so it looks like this works reasonably good for this example. And another example is the D2 lattice gauge theory simulation. So in this case, this is Hamiltonian. Then this is the second term corresponds to the electric field. Then this parameter F controls the presence or absence of this electric field. Then if this F equals 0 corresponds to the deconfinement phase, the non-zero F corresponds to the confinement phase. So the right-hand plot showing this is a plot from different paper done by maybe trapped ion or some atomic system. The vertical axis is the time, and the horizontal axis is a matter site. Then starting from a given matter site, then by doing this time evolution using the, for example, spectral decomposition, the confinement case, this the matter field propagate to the nearest neighbor site. The confinement case is confined within the given the qubit. So we try to do something similar by generating this quantum state using the spectral decomposition of this Hamiltonian, then do the time steps by changing the mass parameter and also this confinement parameter F, then see whether we can classify whether the time evolved state belongs to confinement or deconfinement phases. That's shown on the right-hand plot. So we train the quantum neural network using the quantum state with mass below 1, which is this region. Then try to predict whether the quantum state belongs to confinement or deconfinement phases with the mass above 1. So the training region and testing region different to see whether the quantum circuit can still predict these two states, two phases. And actually, it looks like this works also reasonably good, except very large mass region where we do some kind of a misclassification. So that region is very far from the training region. So that is actually the example that we did for classification or phase recognition for classical data and quantum data. Then, but at this point, we kind of try to revisit the machine learning, let's say, idea. So assuming that the data, the X and Y, are the underlying distribution P, for example, and the data set D is created by sampling this distribution P, if we get some finite data set, this X and Y. So usually the training errors obtained from data set is given like that. So the average of the loss function between hypothesis and true label, Y. But also we can consider the prediction error for unseen test data, which is the average of the loss function, where this hypothesis is somehow constructed from true the input distribution rather than the training data set. So that is what we define here as a prediction error for unseen data. And actually, we quite, of course, we use the training error because that is calculated using the data set given to us. But actually, the most interesting thing is that this prediction error, because we want the machine learning model to be applicable or useful for unseen test data. So finding the hypothesis that minimize the prediction error is a goal of the machine learning. So not just training capability, but also for predicting the unseen test. So we consider some machine learning tasks and model class. So if we consider some given machine learning architecture, this architecture will enable some certain class of machine learning models, which is denoted by this circle, for example, here. So for given architecture, like parameterized hardware exchange ansatz, for example, then that kind of ansatz can model some certain class of machine learning hypothesis, let's say. Then we want to somehow find the true map H star, which is the true model or true map that faithfully output the true label Y from input data X. And the task of the machine learning is to identify some machine learning model which is as close as possible to this true map under the given machine learning architecture. So, so actually, so far, what we considered some machine learning tasks to classification and phase recognition and so on. But so far, it's probably the problem considered so far were very simple, and the true map could easily fall inside the model class that we consider for machine learning architecture. So, if the problem is so simple, then essentially some chosen machine learning model might be able to be very close to the true map. And probably this is not completely proven, but probably that is the case for the problem we considered so far. But generally, if we consider a more complex problem, then the true map may not necessarily reside in a given model class. Like, this true map may be outside the model class that we get from a given machine learning architecture. Of course, if we consider very general quantum circuit, then that quantum circuit may be able to explore a whole Hilbert space. Then that might be able to capture the true map. But typically, that is the case too general. Then it's very hard to train. And so somehow we want to identify some reasonably trainable machine learning class, which is the goal of the machine learning. But anyway, if we consider this kind of setting, then the best model within the model class may be obtained when the input distribution is used in the training rather than the training data set. Because, because if we can directly use the kind of input distribution which creates a data set, then that will give us better chance to have a better model, which is close to the true map. Actually, if the true map is within this model class, then this best model may be able to coincide with the true map. But in this setting, what we get here is a kind of a closest possible model and within this model class. But since usually the input distribution is usually unknown, we have to use the training data set rather than input data. So the best trained model is likely different from the best model because we have to use a finite data set. So if we consider this kind of scenario, then we will need to think three different sources that contribute to errors. Or here, like if we use the training data set, then there is the errors coming from optimization of the machine learning model, which may depend on the optimization algorithm. Then the difference between this best model and best trained model is considered to be the estimation error, which I will describe a bit later. Then for the given machine learning architecture, there may be some model error coming from the choice of the machine learning architecture that we consider for that problem. Of course, the ideal case is that if the true map is within this model class, then all these errors may be zero, which is the best ideal case, but that's typically not the case for, at least for realistic problem. So first, this optimization errors, this coming from how this machine learning model is actually optimized. Then for that, insufficient training could be an important source of optimization errors. Then it's very well known that the training of parameterized quantum circuit generally becomes difficult with increasing system size, the so-called Banach plateau problem. So typically, we measure some observable under the parameterized quantum state, so U row, U dagger. The U is either the operators with a parameterized quantum circuit. Then this cost function or loss function is actually exponentially concentrate to a certain fixed value, or the gradient of the cost function with respect to some parameter in the quantum circuit also vanishes with the increasing system size. So in a picture like that, if we consider the small number of small system size, this cost function landscape is this kind of slope where we can find, hopefully we can find some global minimum for this cost function. But if this kind of cost function gradient vanishing occurs with the increasing system size, then this cost function landscape becomes very flat. So it's very hard to find the global minimum in this case, in this landscape. So actually, we our student, PhD student, actually tries to analytically understand the Banach plateau from one aspect in the parameterized quantum circuit, which is data encoding. So as I said, we first have data encoding unitary, then apply the parameterized quantum circuit to manipulate the quantum state. But by assuming this parameterized quantum circuit is simple, let's say, actually constructed by the tensor product of local operators. Each local operator is a unitary 2 design. So, but since this is a tensor product, there's no Banach plateau coming from this part. But then see whether this data encoding unitary can cause any Banach plateau phenomena or not. So that is the idea. And actually, he tried to provide the upper bound on the variance of the cost function gradient under this circuit structure. And this is the variance of the gradient of the loss function is upper bounded by the product of several terms. And the most important is the last one, which depends on the data encoding unitary. Then he tried to derive the condition where this term does not decay exponentially. But if this term decays exponentially with the system size, then the variant plateau actually occurs. So this is the necessary condition to avoid the variant plateau. Then actually, he tried to derive the condition needed for the depth of the quantum circuit, which is L, then how this should be bounded by the number of qubits in the quantum circuit. Essentially, conclusion is that we have to use a shallow quantum circuit, the logarithmic of the number of qubits in the quantum circuit. So maybe I could probably skip here, but we try to see how the initialization of the quantum circuit is actually useful to avoid the variant plateau, because there is a separate study by other group who is trying to see whether this parameter initialization can actually help mitigating the variant plateau. Like this idea is coming from the many body localization in the condensed matter physics. So somehow constraining the parameter range within the narrow range, like 0 to 0.1, and then the gradient of the cost function stays at large value, independently of the system size, like shown on the right-hand plot. Of course, if we use the global operators for the measurement, the variant plateau can still occur. But if we use the local operators, then this kind of specific parameter optimization, parameter initialization of the parameter might be able to avoid the variant plateau problem. Then actually now he's trying to investigate this estimation error, which is bounded by the generalization error, how the trained machine learning model can be generalized to unseen test data. So now we are trying to see whether this parameter initialization technique can influence the generalization error for machine learning, quantum machine learning model. Then on the last one is a model error, which is typically hard to quantify because typically it's very hard to know what the best model is for a given problem unless the problem is very general or very specific. But some cases, some prior knowledge about the problem is quite useful in building the machine learning model, because if we know some problems have some particular properties, then if we can put that in the machine learning model as an inductive bias, then the model error may be reduced. So one idea here is that the symmetry of the problem at hand is actually useful information to build an efficient machine learning model. So we consider for the symmetry in the machine learning setup, because the symmetry is very, let's say, very popular in physics, particularly particle physics, because the Lorentz symmetry and permutation symmetry and parity and so on. But typically, this kind of a symmetry incorporating such a continuous symmetry in the quantum setting, quantum machine learning, is not so obvious. Then actually one of our postdoc members tried to investigate the generic quantum neural network architecture to efficiently encode rotational symmetry and permutation symmetries by using inner product as the input, because inner product is a rotational symmetry. And also he tried to apply the scoring method make quantum gates invariant against the permutation of the input. Okay, so that is a quantum machine learning model that we developed for this equivariant quantum machine learning, which preserve the rotational symmetry and permutation symmetries. Then applying this quantum circuit to the classification of the Higgs to a 4-lepton final state as a benchmark. Then he managed to demonstrate that right-hand plot showing again the classification accuracy on the vertical axis, and this a false positive, which is let's say the classification accuracy for the background event. So the top left corner is as we go to the top left corner, that is the best model. You see there's a black line coming from the mascot, which means that applying the invariant mascot on the reconstructed 4-lepton mass. So this classification of Higgs event, so there's very narrow peak corresponding to the Higgs mass. Then applying the mass window cut, that is quite, of course, a common technique in high-energy physics, which is pretty much very optimal. But by using this quantum circuit without giving any information about Higgs mass, but doing that, this symmetric machine learning model, performance of this model is very close to the mass window cut, which is quite optimal. So then actually this model demonstrated that this training is very efficient because the number of parameters is very small, and also we didn't see any indication of baryon plateau, even though we measure all the qubits like a global observable, but still looks like we don't see any indication of baryon plateau so far for the given system size. Okay, so so in a recent, actually for the last 1 or 2 years, there is okay, even though we see several interesting features or some promising results from quantum machine learning, there is the skepticism around the variation QML approach because the quantum machine learning model with a provable absence of baryon plateaus in the literature so far might be able to be simulated classically. So that was actually claimed in this paper. So they argue that operator actions in the baryon plateau free quantum circuit are likely constrained in the polynomially large subspace. So then the classical computer, like the classical algorithm, can simulate such operator actions. Like, for example, the Hamiltonian variational ansatz, which is a quantum circuit that is constructed kind of reflecting the structure of the Hamiltonian. But in this case, if the Hamiltonian is expressed as a sum of the local terms, then if this local term is kind of low weight Pauli operator, like acting only on the limited number of qubits, then the problem class, which can be addressed by this ansatz, is likely simulated classically. So, so that is something being under active discussion in the community for quantum machine learning based on the variational approach. And also, even more recently, there's another paper coming up, and they argue that the operator action of the quantum convolutional neural network, which we use for phase recognition, can be classically simulated. But again, the reason is more or less similar to the QCNN avoid baryon plateau because it processes only the information encoded in the small subspace using the low weight observable of the input state. So, so if that is true, the problem that the community considered so far is probably addressing or using the quantum state only in a small subspace to avoid the Barren plateau. So now we are trying to investigate extension to more non-trivial input state or larger quantum system. So one of our postdocs is trying to investigate the dynamics of a confined and deconfined phase in the one-dimensional lattice gauge theory using 25 lattice site corresponding to roughly 50 qubits. So this is just so what we are trying, whether quantum machine learning can be still useful or beneficial for learning large-scale quantum system. Okay, so since I don't have much time, so I already talked about some quantum simulation studies, like the ground state preparation for Shinga model. So maybe I will skip this part. And actually, the quantum dynamics is also quite interesting and potentially non-trivial application of quantum computer. Like simulating the quantum many-body system is very promising area for to demonstrate some usefulness or advantage. So one of our members also try to do this again using the one-dimensional U1 lattice gauge theory, which is a Shinga model. So in this case, he tried to prepare some ground state using variational quantum eigensolver, then turn on this electric field by changing this theta parameter at t equals 0, then do the time evolution of the ground state. Then see whether we can see some effect like expected from like this Schwinger effect by doing this quench dynamics. So for this simulation, he tried to use a variational quantum simulation based on the McLachlan's variational principle. So instead of directly evolving the quantum state, here the idea is to do the time evolution of circuit parameters, then measure this parameter-dependent quantity, then solve for this parameter evolution using a classical computer. Yeah, so that is the idea. Then by doing that, usual kind of time evolution of total steps, if we go to the further longer time steps, the circuit becomes longer. But by doing this parameter evolution, then the circuit depth can be fixed. So we might be able to simulate, let's say, ideally the longer time evolution using the fixed quantum circuit, fixed depth quantum circuit. But there is still some limitation because we have to measure the quantum state multiple times, actually the quadratically with a number of parameters and so on, like this equation. But nevertheless, this could be a potential useful algorithm for near-term quantum simulation. And actually, this is what he got. The left-hand plot showing the fidelity with respect to the truth truth state from exact diagonalization, and the right-hand plot showing the electric field as a function of time, the evolved time. Then starting from some non-zero electric field, then as time goes, the electric field goes down, which could be interpreted as the creation of particles coming from this Schwinger effect. But anyway, this is the first step toward more complex non-trivial simulation as we increase the system volume and so on. And actually, another example is actually one student tries to simulate the dynamical phase transition, again, using the Schwinger model. Like, okay, so there's no time, but idea is to change these theta parameters significantly. Then this strong quench could create a dynamical phase transition. That is the thought in the paper. So he tried to do something similar using VQE plus VQS approach. First create a ground state, then do the time evolution by changing the theta parameters significantly, then see whether this kind of a kink structure can be seen. But since the system size is quite small, like 4 qubit, we can only see this analytical curve, not exact kink. But so this is still very preliminary work, and actually we want to continue this study in some way. So that's something we consider in the future. So maybe last 10 minutes, I will briefly talk about the Qubit technology as a sensing device. Because we think, for example, superconducting qubit is a quite powerful probe to nature. For example, this kind of a typical setup of a qubit, like there is a Josephson junction, which creates a nonlinear inductance of a small electric circuit. Then this big gray part corresponds to to the capacitor, which is create a parallel kind of circuit to the Josephson junction. By creating this small electric circuit, this actually behaves like a nonlinear superconducting qubit. Then why this is useful is that this operates obviously in the low superconducting temperature, so like a millikelvin regime. Then we can access very low threshold for the transition between zero state and ground state and excited state. And also the qubit sometimes becomes potentially have long lifetime, long coherence time, which is the order of 100 microseconds for the least dense quantum device. And we can do some non-demolition measurement on the quantum state. So also by considering this kind of structure, like not very small, like a kind of mesoscopic scale, like this distance between the capacitor plate is the order of 100 micron, then this kind of device can have large EDM. Then this could have very strong coupling to the electromagnetic field, which is much stronger than the single atom. So this property can be used as a sensing device. So if you are interested, you can find more details or more recent results, and they are all presented in the Partners Workshop last month by our group members, students, and young staff members. So if you are interested, please take a look at their talks and posters. And here I just highlight one of them, which is using the superconducting qubit, then actually direct excitation of a superconducting qubit to search for dark matter. Because as I said, if a qubit has a strong coupling to photons, then actually microwave photons converted from dark matter, like a dark photons, might be able to directly excite the qubit from ground state to excited state with some probability. So in that case, if this photons coming from dark photon without magnetic field, then the current superconducting device can be just used as a quantum sensor. But this is still motivated because superconducting qubit typically operate in a microwave regime, which is a gigahertz in the frequency. And there is a well-motivated dark matter candidate in this mass region. And also another example, okay, this is what I said, the superconducting qubit has a strong coupling to the microwave photons. So this could be a sensing. And so I just want to mention that they are actually creating our own qubit and cavity for this experiment. This the capacitance and then this junction by using, in this case, probably aluminum or niobium, then creating Josephson junction. Just two master students are working on that in the clean room and put this circuit on the wafer and so on. So these are members working on this. And so in order to, but you know that the transition frequency of qubit is fixed for a given qubit. But in order to scan the wide mass range, we have to modulate or change the qubit frequency. So in order to do this, currently we are trying two approaches. One is based on Qubit, which is directly injecting the magnetic flux to the qubit. Then this will change the energy, Josephson energy on the qubit, then changing the energy gaps. So in order to do this, this is a cavity, and we put the qubit inside the cavity, then put this a coil around the cavity to apply the magnetic field by the electric current. Another approach is to use the so-called AC stack shift, which has actually helped us to change the qubit frequency by injecting some actual photons with a resonant frequency in the cavity. So what's shown on the right is actually what we get from our experiment. So by injecting some photons slightly of resonance from qubit frequency, then we can scan the qubit frequency by looking at the VNA output from the cavity. Then you see the qubit frequency actually changes. So by using these two techniques, okay, so that is the detail about the experiment. First, we need to read out the qubit state, either ground state or excited state, by looking at the frequency of the cavity. This is so-called this first readout, which is also used for quantum computer. But for example, if the qubit is in the ground state or excited state, the cavity frequency is slightly shifted with each other. Then we can identify whether qubit is excited or not. The right-hand side showing the experimental procedure. So we first qubit is initialized to the ground state, then wait some time during the coherence time, then measure the qubit to see whether it's excited or not. Okay, then maybe I will just directly skip to this is the first result from direct qubit excitation experiment. So we tried this AC stack shift approach and Qubit case. But essentially, we measure only the 16 hours for this case and the 23 hours for Qubit qubit by changing frequency for both methods. But you see some kind of jumping up on the left plot, but this is just due to fluctuation. And also for the Qubit case, there is some fluctuation, mainly coming from some background, coming from thermal noise. So there is no signal in this plot. But just plotting the limit on the kinetic mixing extracted from this equation. So by this excitation probability, by measuring this probability, we can get a limit on this kinetic mixing of the dark photon for the given parameter of the quantum device. So this is a limit. So of course, our sensitivity is limited. This dark gray region is coming from constraint from cosmology, and this light gray region is already excluded by other experiments. So we are still kind of limited, but this is just a first experiment. Then once we can improve the quantum device, like increasing the capacitance or increasing the coherence time of the qubit, currently the qubit is roughly the order of 5 to 10 microseconds for the Qubit case. But if we can increase to like after 30 microseconds, then operate this experiment for longer time, then we might be able to exclude this light blue region. So we are now working to improve like as I said, qubit design optimization for larger capacitance or larger distance between the capacitance parts. Or we can use some quantum interference effect to enhance the sensitivity. Or eventually we are interested in applying this technique to search for actions by using the magnetic field tolerant superconducting qubit. So they are developing for those devices. So this is just one last slide before the summary. So we are investigating a few things, the application, algorithm, and software and hardware. For the application, as I said, we are mainly working on quantum machine learning and quantum simulation for lattice gauge theory simulation, like a 1D or 2D D2 lattice gauge theory or SU2 simulation. And one of us is trying to develop further on the finite temperature or finite density system. And software side, we are working on the quantum circuit optimization. Then we call optimization tool the ExU, which is our optimization protocol, let's say. And also more recently, one of our staff members, Yutaro Iyama, and student Wonho Jan, have tried to implement actually Qubit using the superconducting qubit device, actually using IBM device. Then they try to apply this Qubit to the Toffoli gate implementation. Then demonstrate that we managed to create a Toffoli gate using Qubit with the existing superconducting device, much longer, very stable Qubit implementation. So if you are interested, please take a look. Then on the hardware side, in addition to this dark matter search for qubit, superconducting qubit, one of us, we are also trying to develop components for large-scale quantum computer, or like a small-scale amplifier, or more efficient or scalable circulator or isolator, which is a crucial component inside the dilution refrigerator. So that is something we are working at ICEP. So anyway, so summary. So I just presented selected results at ICEP, quantum computing application for quantum machine learning and simulation, and for search for dark matter using superconducting qubit. So I hope we could demonstrate some quantum advantage or some quantum computer or quantum device as a useful resource in particle physics or the computational particle physics in the future. Then this quantum superconducting qubit device for dark matter search, there is a new opportunity in the technology development, and hopefully we can discover some new physics using those devices. So that's it. So this is our group members. So they are students, young postdocs, young staff members. They are all working on this project. So, thank you. That's it.
Okay, thank you very much for the excellent talk. And so now it's time for questions. So if you have questions, please unmute and ask your question.
Can I ask a question?
Yes.
Thank you very much for very extensive and very beautiful talk. So, so my first question is about your first part. So you explained the quantum machine learning approach to solve the problem, and so you start with VQE algorithm, and also introduced this this quantum machine learning approach. So how these two are so different each other? So both are using some quantum algorithm, and but maybe classical part is different. Or so this looks like very. This picture looks very similar. So
Yes.
So, sorry for this.
Yeah, indeed. Actually, they are very similar. Like BQE or more generally variational quantum algorithm, where we some input state, we manipulate the quantum state by applying parameterized quantum circuit, then measure some observable. That part is very similar. And quantum machine learning, one notable difference is that we have to somehow encode some data into the quantum state, like a classical data for like a classification or some quantum data to the quantum state. So except that part, essentially VQE or VQA or quantum machine learning it is very similar. Like this second part of the circuit is essentially the same. So that's why VQE I talked about this the difficulty trainability, so-called this barren plateau.
Yes.
Yeah, then that is also applicable to both machine learning.
I see.
VQE and so on. So yeah.
I see. But if we just want to compute ground state energy or just try to find some ground states, but these two algorithms are different each other. Well, very similar.
I think so. Like a ground state. Okay, maybe I didn't prepare much slide, but like for example, this kind of Hamiltonian, we can express this Hamiltonian using unitary operators in the quantum circuit, then generate the ground state. So that is the VQE approach. So yeah, so that is what we typically do using variation method. And the machine learning side, we either use the data encoding unitary, like this one to encode the classical data, or in this example, we try to use the VQE to create some input quantum state, like a ground state, then put that into the quantum circuit. So, in that case, just the unitary operators to create input state with the VQE. And yeah.
I see. Thank you very much. So one more question is that about your latter part about quantum sensing. So
Yes.
so because the first time, I think that part is probably go fast anyway. So sorry for this.
About that. Yes.
But I just so using superconducting qubit, so you detect dark photon. I think in my
Yes.
You said some photon and it's converted into dark photon, and then you detect this photon, dark photon, in your device.
Yeah. So
I just want to know how exactly you detect this photon.
Yeah. Okay. Yes. So first of all, it's dark photon, which is this A prime in this diagram. But dark photon has some component of the ordinary photon. Actually, that is. Yeah. So the dark photon, So then, with some probability, dark photon can convert to the photon with certain probability by propagating through this cavity, let's say, material. Actually, by changing kind of a So the some component of the dark photon actually convert to the ordinary photon, which is the microwave frequency range.
I see.
Depending on the mass of the dark photon, but then this converted microwave photon can excite the superconducting qubit if this mass of the dark photon is coincide with the transition frequency of the superconducting qubit. So that is.
I see. So you can change this. Omega, your excited energy.
Yeah, omega is excited energy. Yes.
So you can search against different range of mass.
Yes.
I see.
So we have to change like omega, or we have to change the energy gap between the ground state and excited state. So then the idea here is to use these two techniques to change.
Yes.
Yeah.
Understand you get a final, graph somehow. Some region is excluded.
Yeah.
It shows
Yeah, it's very
that
very small, very narrow region because the frequency kind of the range we can change. The frequency is still quite narrow, like a squid case. It's only like 10
I see.
megahertz, and AC Stark shift case is actually very narrow, like I don't know, 50 kilohertz or something like that. So, but so the ideally we want to span much wider mass region. So in order to do this, we have to consider. There are a number of improvements that we can do for that. Yeah.
I see. Thank you very much. Yeah.
Sure.
Any more question? Yeah, I have also a similar question to Tadashi. So it's in this slide, okay, so you explain about the quantum device and so with which you search for the dark matter. So is this kind of experiment done on tabletop, or so do you need very huge devices?
Right. So I don't know if you have, I have some. So yeah, actually the device itself is like this small, like we just create all these cavities like the order of centimeters, and superconducting qubits obviously very small, but then put that in a dilution refrigerator, which is in this right-hand picture. Yeah, so this is just a room-size device, and yeah, so this is just a human size device. Of course, there are other room temperature electronics, all these control device for microwave and so on. So actual experiment is done inside a single room, but all the experiment equipment actually occupy pretty much a single room. And we use mainly we use this device located in the low temperature, I don't know, cryogenic center, let's say, located in the near next campus. And yeah.
Okay, thank you so much. And also, I have another question. So, do you have any other application of quantum device to particle physics?
So for what physics?
Particle physics, high energy physics.
So far, essentially, we consider mainly for dark matter search. Then another idea is like this cavity horoscope experiment. So the example which I showed before is we directly measure the excitation of qubits. But another way to detect like a dark photon is, as I said, the dark photon can be converted to the ordinary photon by passing through this cavity material. Then this photon can be stored inside the cavity, then just read out this stored photon with then that can be the detector. Of course, this itself is pretty much not quantum, but typically, people try to use this large scale cavity, then store as many photons as possible from dark photon, then amplify the signal for detection. And for this, we can also use the qubit to change the frequency of the cavity in this case, because that is the actual example here. So if we have cavity and superconducting qubit, then they are interacting to each other. So in this system, the Hamiltonian is given by this so-called James Hamiltonian. Then by changing the qubit frequency, just by applying the magnetic field, which I explained before, then by changing the qubit frequency, then the cavity frequency can be also changed depending on this interaction between the two systems. So from that, we can actually, by changing the qubit frequency, we can also change the cavity frequency. Then we can scan the different mass region, mass range of the dark photon. Actually, this is a bit old result, but here the procedure is that yeah, so by changing the current on the coil surrounding the qubit, they measure the transmission rate of the microwave going inside the cavity and coming out from the cavity. Then repeat these steps. We can scan the frequency of the cavity like that. Then okay, this is a bit old, but yeah, I don't have actually the result, but if you see this talk by Nakazono-kun, who is our master student, he actually presented his first result from cavity, the horoscope experiment. Then actually we managed to exclude new parameter region, still narrow range, but yeah, so that's something we are using, cavity and superconducting qubit. And I think some of them have other ideas to apply this kind of technique to another application of particle physics. So if you are interested, I suppose maybe we can discuss further how this kind of technique is applicable to.
Yeah, thank you very much. So any more questions?
By the way, I should have mentioned that this Xion Chen, who is now in the Kyoto University, actually he showed very interesting and clever idea to use a superconducting quantum computer as a quantum sensing device, quantum detector. So so actually, superconducting qubit is a nice quantum device. Then, like IBM quantum computer has a much larger qubit, like 100 qubits. Then sometimes this can also work as a detector. Then just by doing some kind of a sophisticated measurement techniques, to wait some time, the measure the qubit, whether it's excited or not. Then actually, he tried to demonstrate how the existing superconducting qubit quantum computer is actually usable. So in practice, it might be a bit difficult to extract the limit, but at least it's actually useful to identify whether the signal is present or not. So but anyway, if you are interested, please take a look at this poster, which is it's a very interesting idea.
Thank you. So any more questions? Okay, so if not, let's thank Professor Terashi again.